You're falling right now. Not metaphorically, literally. The earth beneath your feet is plummeting through space at over 100,000 kilometers per hour, constantly falling toward the sun but moving just fast enough sideways that it keeps missing. That's what an orbit is, a perpetual fall. And you've been falling your entire life without ever hitting the ground. Everything in our solar system is caught in this same elegant trap. Moons fall toward planets. Planets fall toward the sun. And the sun itself falls toward the center of the Milky Way, dragging its entire family along for the ride. It's a hierarchy of gravity, a nested architecture of objects bound together by the weakest force in the universe, and yet the only one that matters at these scales. But here's what most people never think about. Why does our solar system look the way it does? Why are the inner planets small and rocky, whilst the outer ones are massive balls of gas? Why is there a belt of rubble between Mars and Jupiter? Why does everything orbit in roughly the same flat plane, like water swirling down a drain? The answers reveal something extraordinary. Our solar system isn't random. It's a machine assembled by the same physics that builds every star system in the cosmos. And when you understand how it was built, you start to see patterns that repeat across the universe, from the rings of Saturn to the spiral arms of galaxies. This is the architecture of the solar system, and it begins with a single violent collapse. 4.5 billion years ago, there was no sun. There was only a vast cloud of hydrogen and helium, laced with traces of heavier elements forged in the death throes of ancient stars. This cloud drifted through the galaxy for millions of years, cold and formless, until something disturbed it. Perhaps a nearby supernova sent a shock wave rippling through the region. Perhaps the cloud simply grew dense enough that gravity took over. Either way, the collapse began, and once it started, it couldn't stop. Gas fell inward, faster and faster, spiraling as it went because the original cloud had the slightest rotation. As material compressed at the center, it heated up, pressure built, temperature climbed, and when the core finally reached 10 million degrees, hydrogen atoms began fusing into helium, releasing energy in quantities that defy imagination. The sun ignited. What you see when you look at the sun isn't fire. Fire is a chemical reaction, combustion. The sun is something far more fundamental. It's a thermonuclear furnace converting 4 million tons of matter into pure energy every single second, and it's been doing this continuously for 4.5 billion years. The light warming your skin right now left the sun's core 100,000 years ago, bouncing between atoms so dense that even light struggles to escape. When it finally reaches the surface, it takes just 8 minutes to cross the void to Earth. But the sun doesn't just provide light and heat, it dominates. It contains 99.8% of all the mass in the solar system. Everything else, every planet, moon, asteroid, and comet, all of it together makes up the remaining 0.2%. Jupiter, the largest planet, could fit inside the sun over 1,000 times. Earth, you could fit 1.3 million Earths inside and still have room. This dominance isn't just about size. The sun's gravity reaches out across billions of kilometers, holding objects in orbit that are so distant their light takes hours to reach us. The Voyager probes, launched in 1977, are still technically within the sun's gravitational influence, even though they've crossed into interstellar space. They won't fully escape for another 30,000 years, and the sun doesn't sit quietly at the center. It breathes. Its surface churns with convection currents that create sunspots and solar flares, explosive events that can hurl billions of tons of charged particles into space. This solar wind streams outward at 400 kilometers per second, carving a bubble in the interstellar medium called the heliosphere. Everything inside that bubble, everything we call the solar system, exists within the sun's breath. There's something else the sun did that shaped everything to come. In its violent youth, it burned hot and fierce, blasting the inner solar system with intense radiation. This radiation stripped away lighter elements, hydrogen and helium, from the region close to the sun. Only rock and metal could survive that heat. But further out, beyond a boundary called the frost line, temperatures dropped low enough for ice and gas to accumulate. This single fact, this temperature gradient, explains why we have two fundamentally different kinds of planets. The sun created the conditions for everything that followed. It provided the energy, the gravity, and the sorting mechanism that determined what could exist and where. Every planet, every moon, every ring system is downstream of decisions the sun made in its first few million years. And in the next chapter, we'll see what emerged from that cosmic sorting, starting with the small, scorched worlds closest to the furnace. The four inner planets share a common heritage. They formed from the same disk of debris that circled the young sun, assembled from dust grains that collided and stuck together over millions of years. But despite their shared origin, each one took a radically different path, and the differences reveal just how narrow the conditions for a habitable world really are. Mercury sits closest to the sun, a small, dense world baked by temperatures that swing from 400 degrees during the day to minus 180 at night. It has almost no atmosphere because the sun's radiation and solar wind stripped it away long ago. What remains is a cratered surface that looks remarkably like our moon, frozen in time since the heavy bombardment era 4 billion years ago. Mercury is what happens when a planet forms too close to a star. It survives, but barely. Venus comes next, and it's a cautionary tale. Similar in size and composition to Earth, Venus should have been our twin. Instead, it became a vision of hell. Its thick carbon dioxide atmosphere traps heat so efficiently that surface temperatures reach 470 degrees, hotter than Mercury despite being further from the sun. The atmospheric pressure is 90 times that of Earth, enough to crush a submarine. Acid rain falls from sulfuric clouds, but evaporates before reaching the ground. Venus shows what happens when a greenhouse effect runs away completely. Some scientists believe it once had oceans, perhaps even conditions suitable for life, before the feedback loop took over. Then there's Earth, the anomaly, the one that got everything right. We orbit in the habitable zone, that narrow band where liquid water can exist on a planet's surface. We have a magnetic field generated by our molten iron core that deflects solar radiation and protects our atmosphere. We have plate tectonics that recycle carbon and regulate temperature over geological timescales. And we have a large moon that stabilizes our axial tilt, preventing the wild climate swings that would make complex life impossible. None of these features are guaranteed. Each one required specific conditions, and Earth happened to have them all. Mars represents the other failure mode. Smaller than Earth, it cooled faster, and its core solidified. Without a liquid core, there was no magnetic field. Without a magnetic field, the solar wind slowly stripped away its atmosphere over billions of years. Mars once had rivers, lakes, possibly even a northern ocean. The evidence is carved into its surface, ancient river valleys and mineral deposits that only form in water. But that water is gone now, either frozen in polar caps and underground ice, or lost to space entirely. Mars shows what happens when a planet is too small to hold on to its atmosphere. 4 worlds, 4 outcomes. Mercury, too close. Venus, too thick. Mars, too small. And Earth somehow threading the needle. The rocky planets are a gallery of possibilities, a reminder that habitability isn't just about distance from a star. It's about size, composition, magnetic fields, atmospheric chemistry, and perhaps a fair amount of luck. But these small rocky worlds are only half the story. Beyond Mars lies a boundary, a belt of rubble marking the transition between 2 fundamentally different kinds of planets. The frost line changed everything, and on the other side of it, worlds grew to sizes that dwarf anything in the inner solar system. Between Mars and Jupiter lies a graveyard. Millions of rocky fragments orbit the sun in a band we call the asteroid belt, remnants of a planet that never was. For centuries, astronomers assumed this was debris from a world that shattered, perhaps destroyed by some ancient collision. The truth is stranger. There was never a planet here. Jupiter wouldn't allow it. When the solar system was young and planets were still forming, Jupiter grew massive quickly. Its gravity dominated the region, stirring up the orbits of nearby materials so violently that objects couldn't gently collide and stick together. Instead, they smashed into each other at high speeds, breaking apart rather than building up. The asteroid belt is what remains, a zone where planet formation was permanently interrupted by a giant neighbor. But the asteroid belt marks something else, something more fundamental. It roughly coincides with the frost line, that critical boundary where temperatures dropped low enough for water ice to form. Inside this line, only rock and metal could survive the sun's heat. Outside it, ice became a building material. This single fact reshaped everything. Ice is far more abundant than rock in the universe. Hydrogen and oxygen, the ingredients for water, are everywhere. Carbon, nitrogen, and other volatile compounds that freeze at low temperatures are common. When you cross the frost line, suddenly there's vastly more material available to build planets, and more material means bigger planets. The frost line created two solar systems in one, an inner zone of small, dense, rocky worlds starved of building material, and an outer zone where ice and gas accumulated into giants that would dominate everything around them. It's not a coincidence that the four largest planets all orbit beyond this boundary. The physics demanded it. This divide also determined chemistry. Inner planets are made of silicates and iron, the materials that could withstand the young sun's fury. Outer planets contain those same rocky cores, but wrapped in vast envelopes of hydrogen, helium, water, ammonia, and methane, all the compounds that were too volatile to survive closer in. Even water on Earth may have originated from beyond this line. Our planet formed in a region too hot for ice, so where did our oceans come from? Many scientists believe comets and asteroids from the outer solar system delivered water to Earth during the late heavy bombardment, crossing the frost line billions of years ago to seed a dry world with the ingredient for life. The asteroid belt isn't just a failed planet, it's a marker, a boundary monument separating two regimes of planet formation. On one side, scarcity and survival. On the other, abundance and giants. Cross that line, and you enter a different solar system entirely, one ruled by worlds so massive they could have become stars themselves. Jupiter waits on the other side, and it changed everything it touched. Jupiter is not a planet in the way Earth is a planet. It's a failed star, a body that accumulated so much mass it nearly ignited. Had it been roughly 80 times heavier, hydrogen fusion would have sparked in its core, and we would live in a binary star system. Instead, Jupiter sits at the threshold, too massive to be ordinary, not quite massive enough to shine. This near miss shaped the entire solar system. Jupiter formed early, within the first few million years, vacuuming up gas and dust before other bodies had a chance. Its gravity sculpted the asteroid belt, ejected countless planetesimals into the outer darkness, and may have prevented Mars from growing any larger. Some models suggest Jupiter even migrated inward during its youth, scattering material throughout the inner solar system before Saturn's gravity pulled it back outward. The solar system we see today bears Jupiter's fingerprints everywhere. But Jupiter's most remarkable feature isn't its size, it's what orbits around it. Jupiter has at least 95 known moons, a miniature solar system in its own right. The four largest, the Galilean moons, are worlds unto themselves. Io is the most volcanically active body in the solar system, its interior constantly churned by tidal forces from Jupiter's immense gravity. Europa hides a global ocean beneath its icy shell, kept liquid by those same tidal forces, and many consider it the most likely place to find extraterrestrial life in our solar system. Ganymede is larger than Mercury and has its own magnetic field. Callisto is ancient and cratered, a frozen record of the early solar system. Saturn offers a different kind of spectacle. Its famous rings, visible through even modest telescopes, are made of countless chunks of ice and rock, ranging from grains of sand to house-sized boulders. The rings are surprisingly thin, only about 10 meters thick despite spanning hundreds of thousands of kilometers. They may be young by cosmic standards, perhaps only 100 million years old, the remnants of a moon or comet torn apart by Saturn's gravity. In another 100 million years, they might be gone entirely, slowly raining down onto the planet below. Saturn also hosts Titan, the only moon in the solar system with a dense atmosphere. That atmosphere is mostly nitrogen, like Earth's, but Titan's surface is so cold that water ice behaves like rock and liquid methane fills lakes and rivers. It rains methane on Titan. Dunes made of organic compounds stretch across its equator. In many ways, Titan resembles a frozen version of early Earth, a laboratory for prebiotic chemistry waiting in the outer solar system. Together, Jupiter and Saturn contain over 90% of the mass orbiting the Sun outside the Sun itself. They're the architects of the outer solar system, their gravity having shaped the orbits of everything from asteroids to comets. They may also have protected the inner planets by deflecting incoming debris, acting as cosmic shields during the solar system's violent youth. Or they may have caused that violence in the first place by stirring up the orbits of smaller bodies. The debate continues. Beyond Saturn, the solar system grows stranger still. Two more giants wait in the darkness, worlds so distant they weren't discovered until the modern era, and so different from Jupiter and Saturn that they required a new category entirely. Uranus and Neptune are the forgotten giants. They orbit so far from the sun that even traveling at the speed of light, it takes hours for their glow to reach us. Uranus wasn't discovered until 1781, Neptune until 1846, and no spacecraft has visited either since Voyager 2 flew past in the 1980s. In an age of Mars rovers and Jupiter orbiters, the ice giants remain almost unknown. They're called ice giants because unlike Jupiter and Saturn, which are mostly hydrogen and helium, Uranus and Neptune contain vast amounts of water, ammonia, and methane in their interiors, compounds that were ices when these planets formed. That methane gives both worlds their distinctive blue-green color, absorbing red light from the sun and reflecting back the blue. Deep inside, the pressure may be so intense that carbon atoms are squeezed into diamonds, raining down through the interior like hailstones. Uranus is the strangest planet in the solar system. It rotates on its side, its axis tilted 98 degrees from vertical. Something catastrophic must have happened, likely a collision with an Earth-sized object early in its history that knocked it over and left it spinning like a rolling ball rather than a top. This extreme tilt creates seasons unlike anything else, each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Neptune is the windiest planet we know. Despite receiving almost no heat from the distant sun, its atmosphere churns with storms that dwarf anything on Earth. Wind speeds reach 2,000 kilometers per hour, faster than the speed of sound. We don't fully understand what drives these storms. Neptune radiates more energy than it receives, suggesting some internal heat source, but the details remain mysterious. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies that includes Pluto, Eris, and thousands of other dwarf planets and frozen remnants. This is the solar system's attic, objects that never coalesced into larger worlds, preserved in deep freeze for billions of years. When comets swing through the inner solar system, trailing their spectacular tails, many originate here, dislodged from stable orbits by gravitational nudges. And even further out, surrounding the entire solar system like a shell, is the Oort Cloud. This hypothetical sphere of trillions of icy bodies extends nearly halfway to the nearest star. Objects out here are so loosely bound to the sun that passing stars can shake them loose, sending them tumbling inward on journeys that take millions of years. The Oort Cloud marks the true edge of the sun's dominion, the boundary where our star's influence finally fades into the interstellar void. Occasionally, something from even further away passes through. In 2017, astronomers spotted Oumuamua, the first confirmed interstellar object, tumbling through our solar system on a trajectory that proved it came from another star. In 2019, Comet Borisov followed, clearly interstellar in origin. And in late 2025, 3I Atlas joined them, only the third such visitor ever recorded. These objects remind us that our solar system isn't isolated. We're embedded in a galaxy where material drifts between stars, carrying the chemical signatures of alien worlds. When you look at the night sky, you're seeing a structure. Not random points of light, but an architecture built by gravity and time. The sun at the center, holding everything together. Rocky worlds huddled close, survivors of the early heat. Giants beyond the frost line, assembled from the universe's abundance. and at the edges, frozen relics and wandering visitors, hints of the larger cosmos we're only beginning to explore. You're still falling, just like the Earth, just like the Sun itself, falling through a universe that built this solar system from collapse and will one day reclaim it. If this mattered to you, leave a like, drop a comment, and subscribe. More is on the way.